Hey, thanks for joining us for this second video in chapter 11, where admittedly I think there's like three fairly distinct topics within this chapter, and we're going to get into the second of those, and that's IR spectroscopy or infrared spectroscopy, which, as we mentioned in the last video, this is a really important technique that's used a lot in like forensic analysis. In some chemical analysis, also in research and stuff like that. Also, like in the airport security that looks for different compounds, right? Like often IR spectroscopy is a key analytical technique because it's really fast and easy. Um, but as we'll find out, the NMR, nuclear magnetic resonance spectroscopy, is a much more powerful and robust analytical technique to figure out the structure of a completely unknown compounds from scratch. And that's kind of the goal that we have. So I want you in the back of your mind, eventually after we finish 11 and chapter 10 as well, the goal is for us to be able to figure out the structure of a completely unknown compound sample based on things like NMR, IR, and mass spec data. Okay, so what does IR do for us? It measures the bond vibration frequency in a molecule, and it's really useful for figuring out what functional group you have in particular, or specifically speaking, what kind of bonds you have. And that's because each bond, right, like two atoms are like always not in the exact same distance, but they're kind of always stretching and moving like that animation, and that vibration frequency is very unique to each functional group. Mass spectrometry fragments the molecule and then after the fragmentation, or often also before the fragmentation, it measures how much the fragment or the ion weighs. So it gives us the mass or the weight of a molecule, which of course is really useful, especially if you can determine the molecular weight of the compound. It's really useful for figuring out the structure of an unknown sample. And then, of course, we're going to talk about NMR, which has to do with using a really strong magnet to sort of align each nuclear particle in the nucleus of an atom so that uh, they can sort of have a predictable behavior. And we'll talk more about that. And NMR, like I said, is really useful because it tells something about the environment of each hydrogen and also carbons, so that you can figure out how those atoms are connected together. It's very powerful. In this semester, we won't talk much about UV spectroscopy, but I mentioned UV also just because the UV, um, which is like right here, as well as IR, and NMR uses radio wave down here. All these are different parts of the electromagnetic spectrum, the light radiation, which, right, that's part, the visible light is part of the big electromagnetic radiation spectrum. And you might recall from Chem, or maybe even from like a physics class, you might have learned this, but certainly in Chem, wavelength and energy are inversely related, right? That just means like high energy radiation has a very short wavelength and high frequency of like vibration. And then a low energy radiation has a very long wavelength and low frequency of wave function, right? And so another way to say the same thing is like this: wavelength and energy are inversely related. And in this particular chapter, we're going to look at molecular vibrations, which give rise to infrared signal. And as we said, that these IR part of the electromagnetic radiation we get to observe from molecules doing like this stretching of the bonds, as well as kind of a molecular motions, kind of like molecules dancing. That's kind of the picture you could have. And but especially most useful are the stretching frequencies when the bonds are like stretching and shrinking and whatnot. Even outside the context of chemistry, I think you've seen some like IR data. That's how you could see, for example, like in the dark, you could see through IR signals, like right, the night vision stuff. Also, like you could look at IR, because IR to see like how the heat is escaping or kept within the house for like evaluating insulation and stuff like that. But anyway, what's really relevant for us is the, like we said, the IR stretching. So I want you to be picturing um, the chemical bond between two atoms that are stretching and shrinking and whatnot, kind of like a spring would, right? If you imagine like a slinky type of a situation, right? Like if two balls are stuck together with a slinky in between, that's kind of what I want you to picture. And while I don't need you to remember the formula or anything like that, unless you move on to physical chemistry later, the frequency of this stretching vibration can be described like this. And the reason why I wanted to share this with you is because on the top numerator, we have the force constant, which has to do with the bond strength. The stronger the bond, the higher this number is. And the higher that F is, right, the higher the frequency. And hopefully this is pretty self-explanatory or not intuitive. It's intuitive because stiffer the spring is, right? Like if you stretched it and then let go, it'll vibrate. And that's going to be higher frequency of vibration if the spring is stiff or stiffer. Now, if it's like a softer spring, when you stretch it and then let go, you could, even physical thought experiment, you could imagine the spring would vibrate at a much slower frequency, right? So that's what that's talking about. So what does that have to do with chemistry? Well, triple bond is much stiffer because, well, there's 3 bonds involved than double bond, which is still stiffer than a single bond, and that's reflected in these wave numbers, which is another way of measuring the frequency. Okay, so the frequency of vibration is higher with stiffer bond, lower with less stiff bond. Now, in the denominator is the mass, right, of the two atoms connected together by the bond. And so, as you can imagine, if you're dangling a slinky attached to like a light atom, it would vibrate at a much lower frequency. Much higher frequency than if you attached a heavy atom. Right? If you attach something really heavy, it would vibrate. Spring would vibrate at a much lower frequency, and that's kind of what we're showing here. The different masses of the atoms. Okay. So frequency decreases with increasing atomic mass. Like we said, frequency also increases with increasing bond energy, or roughly you could think of it as like going from single second to triple bond. Okay, and so another way to say that kind of mathematically is like this wave number, which is again is another way of saying frequency is sort of proportional to energy. And these are different types of vibrational modes that a molecule can have, whether it's symmetric stretching or anti-symmetric stretching, or they can also do other motions like scissoring, which is this type of motion, or rocking, right? Like at this point, like it's almost like a demonstration of like a different dance moves, wagging or twisting. And so if you didn't know, molecules at any point, it's always kind of using all these different dance moves all at the same time. And now, of these different types of modes of vibrations or motions, the first two, symmetric stretching and anti-symmetric stretching, are most useful in terms of IR spectroscopy because they're often unique to functional groups. Different functional groups would have a very unique vibration frequency of doing symmetric or anti-symmetric stretching, and that's what we're going to be focusing on. And they kind of break down like this, right? These are the wave numbers or frequencies that are really useful for identifying functional groups, whereas these lower wave numbers or frequencies, we would often call those the fingerprint region, because they're kind of unique to the very sort of unique motions, or you could almost say dance moves, that molecules have, like those scissoring and rocking type of a movement, right? So, because of that, no two molecules have exactly the same IR spectrum, technically, and so you could potentially use this to identify a specific molecule. Of course, enantiomers sort of would do the exact same dance moves because they're mirror images of each other. But those very unique things are seen in the fingerprint region. So that gets really complicated. So in our class, we're not going to really look at that area at all. We're going to look at this area of the spectrum, and that will be kind of just predictable based on what functional groups you have. And like I said, wave numbers, it's a different way of expressing the frequency. The wave number is just another way of saying how many waves there are of the electromagnetic radiation wave function, how many waves there are in a centimeter. And it's just another way to express frequency, because the more waves there are in a centimeter, right, the higher the frequency, right? So I want you to be picturing something like this. If a lot of waves fit in a centimeter, it's a pretty high frequency, right? And the frequency, again, is directly proportional to energy, and that's what we just discussed. But the main thing that I want you to know and to be able to discern going forward, especially starting in the next video, is how to discern all the peaks that show up in these IR spectrum. Like I said, this is the fingerprint region. Non-fingerprint region roughly breaks down to three areas. Not surprisingly, the least stiff bonds, single bonds, show up over here with well, I should say not single bonds. The non-stiff bonds show up over here with a low frequency, right? But when you attach just a really light atom like hydrogen to a bigger atom, the because the weight is small, the spring can vibrate at a much higher frequency. So that's up at around 3000 is all hydrogen attached to something, bonds. And then something that's pretty stiff would, of course, give you, even between two heavy atoms, a pretty high frequency vibration, right? Because it's a stiff bond. Less stiff would give you, of course, less of a frequency in this region. So that's what we're going to be looking at. The NH, OH, CH bonds, In this area, we can look at triple bonds. In this area, we would see the evidence of double bonds. Just to give you an example, right? Like here's an example of an IR spectrum, um, and it's given in the transmittance. So if a molecule is vibrating at these wave numbers or frequency, it absorbs IR at that same wavelength or frequency or at that same energy level because it uses um, that energy, right, the exact frequency to do these motions. So the CH stretch shows up here of this alkane molecule. You have the various interesting scissor moves and rock moves and stuff like that over here, as well as some CC action over here, but again, that kind of falls into the fingerprint region. We don't need to really pay attention to that. The main thing we really need to pay attention to is that the CH stretch falls right in the area that we expect for sp3 alkane CH stretch. Okay, so we'll pick up from here in the next video. In the next video, we're going to look at a whole bunch of these IR spectra and go over those different types of wave numbers that you expect for different bonds. I might keep interchangeably saying functional groups instead of bonds, but technically what you're seeing in IR is different types of bonds, not necessarily functional groups, but different types of bonds are kind of unique to each functional group. So in essence, it's kind of interchangeable, but not, or synonymous, but not exactly. So I just want you to kind of be aware of that nuance. And then, of course, in class, we're going to do some practice deciphering what functional groups you have based on spectrum and stuff like that. So, okay, I'll see you in the next video.